Okay, welcome to the next lecture for ES300. Today we're going to talk about nuclear power. So the three quasi-final exam questions for today are: what are the principal advantages of nuclear power as a generating resource? What are its drawbacks? And what is the projected role of nuclear power in the US in the future? So let's start with some really basic physics. So the main energy production process in nuclear power plants is nuclear fission reactions. So there are two pieces, important pieces in a fission reaction. There's fissile material, so this is material that often splits when bombarded with a low energy neutron. One example would be an isotope of uranium with atomic mass of 235 or U-235, and then a neutron. So a neutron is a subatomic particle with no electric charge, and the neutron is what we're using to split the fissile material. And so the splitting, the fission of the fissile material is what creates the energy. So let's look at a single reaction. Off to the left here you see the schematic of a single neutron being shot at a piece of fissile material, uranium-235. When the uranium-235 absorbs this neutron, it becomes excited, and then its nucleus is unstable and it can split. When it splits, this is the fission, it results in a release of energy, as well as the split into lower mass fission products, which are those blue blobs that are shooting off, and then more neutrons. In this case, we see that the fission reaction creates 3 additional neutrons, which are flying off in 3 different directions. And so the key to using nuclear fission as an energy source is being able to sustain chain reactions. And so the way this works is that you have some sort of initial fission reaction that occurs as a result of neutron bombardment of the fissile material. And that's what's shown in number 1. Number 2 shows the result of that initial fission reaction. So we create these lower mass fission products, as well as 3 new neutrons that go shooting out from the fission reaction. So the fate of those 3 neutrons is what we're interested in here. One is absorbed by a non-fissile isotope of uranium-238. So this is a substance that when it absorbs a neutron, it does not tend to, or at least low energy neutron, it does not split. Another neutron is lost off to the right, and then one intersects with another atom of uranium-235, and it causes a second fission reaction. And so that second fission reaction again releases energy, produces fission products, and then results in the creation of 2 new neutrons which go off, fly off in 2 different directions. And in this case, in part 3, we see that those 2 neutrons themselves are responsible for initiating 2 new fission reactions that again release energy, produce fission products, and then even more neutrons. So you can imagine that for every 1 fission reaction, we create 2 new neutrons that go off and initiate 2 more new fission reactions, and you get this chain reaction of increasing release of energy. And so this is sort of the basic premise for the creation of nuclear weapons, where the whole idea was to release as much energy as possible, as quickly as possible, through chain fission reactions. In the case of nuclear power plants, we want to have sustained chain reactions where 1 fission reaction is responsible for initiating additional fission reactions, but we don't want this to be a runaway process where all the energy is released at once. We want this reaction to be controlled. And so engineers can control the rate of a fission chain reaction and decrease it by increasing the presence of substances that are known to absorb neutrons but don't cause fission. So examples would be silver and cadmium. So the fuel that we use in nuclear power plants are those fissile products, the substances that are known to split with a high degree of likelihood when bombarded by neutrons. So nuclear power plants commonly make use of uranium and sometimes plutonium isotopes. We're mostly going to talk about and use as a reference point here uranium-235, which is a common fuel in nuclear power plants. And if you think back to figures I've shown in the past about where we get coal and where we get natural gas, I made a point of pointing out the differences between the countries that are sitting on lots of coal reserves versus natural gas reserves. The countries that have a lot of coal tend to be geopolitically stable, whereas countries that have a lot of natural gas and oil tend to be less so. And you can see from this list, it's sort of a mix of countries that we would consider to be more or less geopolitically stable. So the mining of uranium actually happens a lot like the mining of coal. Uranium starts out embedded in rock, in ore, that can be extracted via open pit or underground mining, as well as what we call in situ leaching. So this is actually becoming a much more prominent mining process. And the way this works is that you have injection wells that are sending down into underground geologic formations some sort of solvent or liquid that dissolves the rock ore that contains the desired uranium, and then that solution is pumped back up above ground to a processing plant where the uranium can be separated from the rest of the substances in the solution that you don't want. So once uranium is mined, whether that's in a rock form or through in situ leaching, it goes through what's called milling. And the whole point of milling is to increase the concentration of uranium in the end product. So uranium ores in the United States at least. So uranium ores in the United States at least typically range from about 0.05 to 0.3% uranium oxide. And so if you're talking about extracting uranium ore via surface mining, that rock is first ground up into a uniform size, and then chemical leaching is performed to separate the uranium from the waste rock, similar to what's happening underneath the ground in situ leaching. And so this process is responsible for separating out a lot of the stuff we don't want in the rock from the uranium which we do want. So the end result is this dry powder consisting of concentrated about 80% natural uranium, which is sold on the uranium market as uranium-308. This is also known as yellow cake, and this is kind of what it looks like. So after the concentrated uranium oxide is produced, we have to enrich it, and all that means is you want to increase the concentration of the uranium that is known to be fissile, right? So that will nearly always split when struck with a free neutron. So naturally occurring uranium consists of about 99.28% of the isotope U-238, which is a lot less likely to split when bombarded with a low energy neutron, and then very little, about 0.71% of uranium-235, which is much more likely to split. And so that's what we want more of is the U-235. And less of the U-238. And again, the reason is there's only certain isotopes of uranium that are more likely to split when bombarded with a neutron, and that splitting process is what releases the energy. So we need a sufficient concentration of the U-235 in order to have a sustained fission reaction. And so the enrichment process just means that we're separating the two different isotopes, the U-235 from the U-238, in order to get a higher concentration of the U-235. And so this is typically done using centrifuges. So centrifuges are mechanical devices that spin really fast and rely on centrifugal forces to separate two different substances based on slight differences in mass. Because if you have two different substances that are slightly different in mass, then different forces will be applied to them. And so they can separate out. And so once you have enriched yellow cake, so this would be yellow cake that has a higher concentration of, for example, U-235, it's then converted into uranium dioxide and baked into hard cylindrical pellets. These pellets are then stacked into tubes of corrosion-resistant metal alloy, becoming the fuel rods that are part of the reactor core. So here are some of the pellets. Here they're stacked into fuel rods, and then those fuel rods are then going into the reactor core, which is the sort of centralized place where the chain fission reactions are meant to occur. Okay, so nuclear power plants in the United States began operating in 1958. At least that was when the first nuclear power plant that was entirely devoted to peacetime production of electricity became operational. This happened at the Shippingport Atomic Power Station in Pennsylvania, right on the Ohio River, on the border of Ohio and Pennsylvania. And so nuclear power plants rely fundamentally on the Rankine cycle. We've seen this before. This is where you have some sort of heat source, whether that's a coal combustion process or natural gas combustion or nuclear fission reaction, providing a source of heat. And that heat is used to boil water, and the steam that results from that is allowed to pass through an open space, and as it expands, it performs work and spins a turbine. That turbine is a coiled conductor that's spinning within a magnetic field, so it generates electric current, which we harvest. That steam is then cooled down back into liquid form and pumped right through the cycle once again. So the main cooling agents here is a condenser coil through which some sort of cold liquid, usually water from a river or lake, is being pumped. So there's different types of nuclear power plants. The most common is called a pressurized water reactor. And so the way this works is that you have two different cycles. So within the containment structure, you have the nuclear reactor, where you have a sustained fission reaction providing a source of heat. So to harvest that heat that is produced by the fission reaction, pressurized water that doesn't boil is pumped through the reactor core. And so it absorbs a lot of the heat from the reactor, and it is then pumped out of the reactor and passed through a steam generator. That water is then heated up into steam. The steam passes through a turbine, generates electricity, and then interacts with some sort of condensing coil or cooling system, which cools the steam back down into water, and that liquid water is passed through that secondary cycle again. So the reactor core is where the fission reactions, heat production occurs. This is typically surrounded by some sort of reactor vessel to keep radioactive material from being released into the environment, as well as a secondary containment structure. So the water is heated as it is pumped through the reactor, and then this removes the heat energy from the reactor, which is used to produce the steam. Steam is run through turbines, which produces the electricity. So the cooling system here is down at the bottom right. So the main function of this is to pump cold water in and turn that steam back into water, which can be pumped back through the steam generator as it interacts with the pressurized water that's heated in the reactor core. The cold water that comes in absorbs that waste heat and then is pumped back out. So this is a similar type of cooling system that we've seen at coal-fired power plants. In addition, many nuclear power plants have evaporative cooling towers, which are used to further reduce the temperature of the cooling water before it's discharged immediately back into a river or a lake. A lot of nuclear power plants face the same issues as coal-fired, steam-based coal-fired power plants, in that they are a source of thermal pollution because they're discharging hot water back into a river or lake, and hot water is able to hold less dissolved oxygen. That means that sometimes surface water bodies, freshwater bodies, immediately downstream from nuclear power plants are subjected to lower dissolved oxygen. Okay, so the nuclear fuel cycle, we've talked about how it's mined and produced. It's mined, milled, enriched, put into pellets and rods and delivered to the nuclear power plant. After the nuclear power plant, after that fuel is used in fission reactions to produce heat, which is transferred to kinetic energy, which is transferred to electrical energy, that fuel becomes, in some sense, a source of waste that has to be dealt with. And the nuclear fuel cycle essentially refers to two divergent possibilities about what happens to that waste, whether it can be repurposed and recycled back in a nuclear power plant, or whether it needs to be disposed of in a more permanent way. So when we talk about nuclear waste, often what we're talking about are the fission products that are themselves not capable of sustaining a fission reaction. So examples would be those lower mass fission products that are sort of shooting out as a part of the fission reaction, as well as other forms of other isotopes of uranium that are less reactive when being bombarded with these low energy neutrons. So example would be uranium-238. And so eventually, when the concentration of these less fissile substances in the fuel rods builds up, that means that there's a lower rate of chain reaction, which means that it's producing less and less energy. And so at some point, the decision is made to replace those fuel rods, and the fuel rods that are taken out are referred to as spent nuclear fuel. So there's two options about what to do with spent nuclear fuel. The first is to try to recycle it, and so this would refer to a closed loop nuclear fuel cycle. So where we're mining and enriching nuclear fuel, using it in nuclear power plants, it becomes spent, so it has a lower concentration of fissile material. But then we can put it through some sort of production process that re-increases the concentration of fissile material, and it can be sent back to a power plant for further use in a reactor. The other alternative, and this is the one that's currently pursued in the United States, is that the waste products from nuclear power plants, that spent fuel, is simply stored on site in a semi-permanent way. So the idea of closing the loop, the nuclear fuel cycle, rests behind the fact that the spent fuel still contains quite a bit of the U-235, so the fissile material and other material that can be converted back into U-235. So these fissile and fertile materials could be separated and recovered from the spent fuel. However, this is not done in the United States. The official reason is that it could present opportunities for bad guys to get some of this nuclear fuel. The other reason it's not pursued at this point is that it can be too expensive. So the current solution is that we have an open loop nuclear fuel cycle where we're storing waste on site at nuclear power plants. They're typically submerged in ponds of water to help absorb some of the heat and buffer some of the radioactivity of the spent fuel. So attempts by the U.S. government to find permanent centralized long-term waste disposal sites have mostly failed. The official and actually legally mandated site is called Yucca Mountain. It's in Nevada, but no waste is being stored there. And in 2009, the Obama administration made plans to close it. So this gives you a sense for where this would be located. Sort of south-central Nevada. And here's a picture of Yucca Mountain from the outside and from the inside. So the safety of nuclear power plants is obviously an important concern. These are some of the most sophisticated and complex energy systems ever designed. And the reality is that no complex system, no matter how well it's designed and engineered, is failure-proof. And there have been a few high-profile accidents at nuclear power plants, including 3 Mile Island in the United States, Chernobyl in the Soviet Union, the Fukushima Daiichi plant in Japan, and then of course Springfield. However, I think it's important also to put these accidents in perspective. So what this figure shows is on the x-axis years, and on the y-axis reactor years of operations in the thousands. And so this gives you a sense for cumulative reactor years of operation across the entire world. So 15,000 years of active nuclear power plant operation, and only 3 really major accidents during this very long time period. So if we're thinking about safety and reliability, obviously it's important to think about the worst case scenario, and the worst case scenario in terms of accidents at nuclear power plants is obviously worse than the worst case scenario at a natural gas plant or even at a coal plant. However, for the most part, nuclear power plants have a track record of reliability and safety. However, as a result of these high-profile accidents, there has been increased attention to safety issues. Probably the biggest impact associated with this increased attention is greater difficulty and time commitment of permitting. And so this has effectively increased the construction cost associated with nuclear power plants.